Plants are the most common and important life form you see every day. Whether you think of the angiosperms with their fruits that range from the cuticles of wheat seeds to the bulky, juicy watermelons, to the gymnosperms like the conifers with their needle leaves and hard pine cones protecting their naked seeds, to the simple bryophytes that bathe in the sun on the surfaces of rocks or the bark of trees. We're so familiar with these organisms, we often forget they play an important role in chemically changing our atmosphere and keeping us and our ecosystems running, mainly because we are so fixated on the delicious flavor of their corn and watermelon and the fauna they raise, so we simply see them as inanimate as the rest of the scenery, no different to the rocks we simply toss aside as we hike. And this is especially apparent when it comes to building fictional worlds. As an example, think of an alien world you are familiar with. Whether it's a fantasy world from pop culture like Avatar, or the realistic takes on an alien world, like Bibelardine's alien biospheres, what kind of life forms do you think of? Typically the fauna, like the human, pterosaur, or horse analogs of Avatar, or the arachnid-like fauna of Bibelardine's alien biospheres. But do you ever consider the flora? But you might think the evolution of plants should be easy and boring. First, you start off with unicellular algae, then it becomes multicellular algae, and then it becomes terrestrial and diversifies into trees. So, this is how plants evolved and will evolve on alien planets. Right? But in actuality, the evolution of embryophyte plants was much longer and complicated, involving the divergence of Viridae plantae into Streptophyta and Chlorophyta, the evolution of a phragmoplast, increasing multicellular complexity in streptophytes, evolution of a vascular system and bryophyte-like ancestors, etc. So for this series, I will only focus on the evolution of alien plants, or just algae in general, using the evolutionary history of Viridae plantae on Earth. How will our algae first originate? How will they diversify in our planet's oceans? How will they become multicellular? Will their progression to land be gradual or sudden? How will they affect the planet's climate? Before we explore everything else, let's take small baby steps and answer each of these questions one at a time, starting with the origin of algae, or the planet in general. A small disclaimer, when I say only focus on plant evolution, I mean only on plant evolution. I won't put too much detail or attention on everything about the biosphere. So anything involving the astronomy of the planet or the fauna of the planet will be simplified or briefly touched upon at best. If you want to see a speculative evolution project that fleshes out the astronomy or the final evolution of an alien planet, go watch Project Rose's Planet Nusku, or Rubia Project, or any other biosphere for that matter. I will only focus on plant evolution for now. So, let's get started. The star we orbit is a Type G star, which lasts about 10 billion years, and its habitable zone will be between 0.9 to 1.2 astronomical units. Our planet is located 1 astronomical unit away from the Sun. Just to keep things safe, and to prevent things from becoming too convoluted, this alien planet will also rotate around a Type G star. The habitable zone in this solar system will also be between 0.9 to 1.2 astronomical units. However, our alien planet will be just near the start of the habitable zone, around 0.95 astronomical units. The gravitational pull of our planet is about 10.70 meters per second squared, and its axial tilt is 24.2 degrees. This planet's moon is about the same size as ours, if not smaller, being around 7.9 times 10 to the 19th power tons. We'll call this planet Latomos Hortus, Lathort for short. Now for the history of the planet. Lathort and its moon were fully formed around 6.2 billion years ago. At this time, Lathort mostly lacks an atmosphere, only consisting of hydrogen and helium, the most common gases in our galaxy. But due to the planet's gravity, most of the elements will dissipate into space. However, on this planet, there are even higher concentrations of uranium and thorium, almost double the amount, with there being 92 trillion tons of uranium underneath this planet's surface, compared to the 40 trillion on Earth. However, uranium and thorium release helium as it decays. Thus, while hydrogen will mostly dissipate, helium may still remain slightly concentrated in this atmosphere, thanks to radioactive decay. But at last, helium will not be the only product released by volcanic activity. Other gases, such as ammonia, hydrogen sulfide, nitrogen, and carbon dioxide, will populate this planet's atmosphere. But later on, during this planet's chaotic beginning, millions upon millions of asteroids will crash into the planet's surface. The asteroids carried water, frozen in its interior, so eventually water vapor joined in as the dominant gases in the atmosphere. This era of chaos lasted until 4.7 billion years ago, when the planet's surface cooled, water vapor condensed, and later formed the planet's oceans. The formation of the planet's oceans will cause an array of chemical reactions between atmospheric gases and water. Carbon dioxide will dissolve into carbonic acid, increasing the ocean's pH. And it also react to calcium at the sea floor, forming calcium carbonate. Methane, on the other hand, will start forming methane clathrate in the ocean's deeper depths, where pressures are high and temperatures are low. But thanks to helium being more concentrated in the atmosphere than on Earth, helium clathrates will also start forming with the methane clathrate. Life itself came about not too long after its oceans formed. The exact origins of life is still being debated, as we don't have an entirely clear image as of now. We do, however, have a clear image on the origin of species. Life around 4.6 billion years ago will mainly consist of prokaryotic life, as there is no oxygen to support any mitochondria-like prokaryotes to support eukaryotic cells, so life will mainly be anaerobic. However, conditions will change rapidly as the evolution of photosynthetic prokaryotes caused the planet's first mass extinction event. Photosynthetic life will use phyclobins for photosynthesis, meaning they'll mostly be red. However, they can also be blue, brown, light green, and pink, similar to rhodophytes on Earth. Initially, oxygen will mostly be absorbed by iron, mostly by the planet's new continents. But after all the iron has been oxidized, oxygen started polluting the atmosphere. It began reacting to methane in the atmosphere to produce the weaker greenhouse gases, water, and carbon dioxide. This led to a runaway greenhouse cooling event. Glaciers formed over the continents, populations were reduced due to cold temperatures, and most of the prokaryotic life, being anaerobic, was killed off by the oxygen. However, eventually conditions will stabilize. As the glaciers melt away, they leave behind pits on the continents caused by their weight. This will form great freshwater lakes fed by mountains at the center of the continent. This is actually how our Great Lakes were formed by the tree of our last ice age 20,000 years ago. After the mass extinction event passed around 4 billion years ago, we see the appearance and diversification of eukaryotic organisms, thanks to the oxygen in the atmosphere. Just like eukaryotes on Earth, they most likely descended from prokaryotic cells that involved a nucleus and membrane-bound organelles, one of them being derived from an endosymbiotic relationship with an aerobic prokaryote that produces adenosine triphosphate for its host. Just like the prokaryotes include a wide array of heterotrophs, hemotrophs, and eventually, autotrophs. The clade we'll be focusing on is called Rubrum phyta. They most likely evolved from eukaryotic cells that formed an endosymbiotic relationship with prokaryotes that perform photosynthesis. Other synapomorphies of this clade are cell walls made of cellulose, flagella, valcule, and starch vessels. Ancestral Rubrum phyta would have had haploid genes and thrived at the uppermost part of the photic zone. But thanks to the freshwater lakes formed by melting glaciers, Rubrum phyta would diverge into two lineages, the freshwater-dwelling Prepterophyta and the marine-dwelling Tetrarhiza. These two lineages will form the most diverse algal lineages on this planet, taking on a variety of unicellular, multicellular, aquatic, and even terrestrial forms. Well, I think that should do it for now. Thanks for watching. In the next episode, we dive into the synapomorphies and diversification of Tetrarhiza, and compare it to the evolution of chlorophytes on Earth. Well, see you soon. Bye.